So our chancellor and our dean has set up these initiatives called Translating Duke Health. One of them is in the area of neuroscience. And the idea behind the neuroscience is to understand what powers the brain has to heal itself. The 7-year-old girl had half her brain removed for a condition called Rasmussen's encephalitis. But you'd imagine that that surgery would leave the child profoundly hemiplegic on the right side and possibly unable to speak. And initially, that is what happens. But the report shows that after 3 years, when this child comes back from follow-up, it is very difficult to tell that anything has happened. She's walking, she's talking, she sees, she plays. And that's half of a brain removed. Yet in a 7-year-old, a very small stroke can have devastating long-term effects. And this brings us back to the beginning where we talked about the Chancellor's initiative for Translating Duke Health, which is to understand what it is about that 7-year-old that allows her to regain almost completely normal function that disappears as we age. We have all, as a group, have committed to this as the cornerstone of what neuroscience at Duke should be.
So we know that brain disorders start in the brain long before symptoms appear. So we're focusing on the very early components of disease, trying to understand both the basic disease mechanisms and the biological mechanisms of resilience and repair that the brain uses to forestall symptoms. We have 3 strategies. One is to support basic science, knowing that many treatments for human disorders have come from the serendipitous discoveries of scientists seeking knowledge for its own sake. The second is to develop a culture of moving that knowledge very rapidly into treatments and cures for human disorders. And the third is to look for very, very early ways to diagnose so that we can treat the disease mechanisms itself rather than simply treating symptoms.
At Duke, we've started to think differently about cancer. We've started to look past the cell division and really look at these changes in the DNA that I think produce a fingerprint which allows us to target these cells very specifically and very potently. For years, we've been treating patients with poisons that sort of stop the cells from dividing. So we had to develop another trick. And that trick was that we used things that the immune system already hates, things like tetanus or polio. And we combined that with these proteins to really signify to the immune system that we wanted it to attack these proteins. And that's the kind of technology that we're developing at Duke today. And then there's Ryan, an entrepreneur from St. Louis. He was a professional golfer. His business in St. Louis was thriving. He had everything. Then he had a seizure. And then he had an MRI, and then he had a brain tumor, and it was a big one, and it was a bad one, the worst kind. So can you imagine the courage for Ryan to fly halfway across the country, to be injected with something we didn't know what it would really do to him, to trust in us that we had hope too, that it might save his life? Well, this is Ryan today and his family. He survived 15 years with this tumor that should have killed him in a year. And I wonder where this legacy of innovation, this path of discovery will lead and whose life it will change next. Could we use these vaccines to treat our children or our grandkids before they get cancer and stop this evolutionary process in its tracks? Wouldn't it be just really cool to do that? Well, I can tell you, if you're part of Duke, you are part of that.